Alright, so welcome back. So what we're going to see here is our first example that is going to involve exponential decay instead of exponential growth. Everything we did so far, like example 4 and example 3 here, we were increasing, we were growing. But here we have a card that's depreciating, so losing value by 7% every single year. So if we're losing 7% every single year, our decay rate is 7% or 0.07 in decimal form. So that would mean that our A value, since it's decay, will be 1 minus that decay rate. So 1 minus 0.07 would be 0.93. So each year it's going to lose 7% of its value. So we're going to represent that with a base of 0.93. Okay, we are told that this car is worth $56,000 new. So at the very start it's worth $56,000. That's going to be our initial value C. We want to know how much it's worth in 9 years. So in 9 years, that's X. What's that value going to be? Our final value Y. That's what we're looking to find out here. So we're going to write our equation, Y equals C times A to the X. Okay, our initial value, we know. We're going to throw everything into the equation here. 56,000 times 0.93 to the exponent 9. Okay, the nice thing about this one is we're looking for the final value. It's already isolated. There's not a lot of algebra we have to do. In fact, there's no algebra we have to do. We just need to run this through our calculator. Be very, very careful when you're doing this. You always want to follow BEDMAS, order of operations. So that would mean exponents come before multiplication. Do not multiply 56,000 by 0.93 first, then take it to the power 9. You will not get a number that makes any kind of sense. Okay, so when you run this through your calculator in the correct order, you should wind up with about $29,000. So let's take a look at our value here. Yeah, so we should get $29,143 and rounded 2 cents. Okay, so that's our first issue, first problem with decay. And again, you see it's very much similar, except we just have to be careful when we're finding our base, that we make sure the base of our power represents decay, so it needs to be less than 1, so we subtract our decay rate from 1. Okay. With that in mind, I'd like you to try B completely on your own now, and again, push play when you're ready to go through it. But this one's very similar to A. Might be a different variable to solve for, but the setup should be very, very similar. Okay, so again, pause it, give it a go, and push play when you're ready to see it. Okay, so hopefully you got an answer like this one. So our starting value, the new car price, is what we don't know. That's our C. It's worth $12,500. That's our final value Y after 7 years, which is X. Again, depreciating by 7%, so our decay rate is 7%, which is 0.07. Subtract that from 1, and you get a base of 0.93. Okay, so we're solving for the initial value C, so we're going to divide both sides of the equation by 0.93, the exponent 7. We wind up with $20,774.44. Okay, so this would probably be a good stopping point if you want to start doing some homework just to try and reinforce it before you continue on to potentially some more challenging examples. So you have your homework here at the end of your lesson. It's from the textbook here on page 261. So you may want to give a few of these a try before you continue on. When you are ready, come back here and we'll just pick up right where we left off. Okay, so again, if you're ready to continue, let's just do a quick recap of what we saw. So in each of these scenarios, I want you to find the value of, at least at the first chart up here, sorry, find the value of the base that you're going to use in the power that's going to be in Y equals C times A to the X. So if we have decay by 13%, what's going to be our A value? Growth by 3.45%, what's going to be our A value? And so on and so forth. And then we're going to go backwards here. So again, just practicing here, I'm going to give you the A value, telling you what the growth or decay rate is going to be. Okay, so take a second and try those first, and then we'll go through them together. Okay, so here are the answers for you to check. Hopefully you got most of them. There might be a few tricky ones in there, but let's just recap here. So first one here, decaying by 13%. Any percentage you get, you have to convert to a decimal first. So you divide it by 100. So for the first one, you're at 0.13. 3.45% when you divide it by 100 gives you 0.0345. 0.3 divided by 100 is 0.003. And 400 divided by 100 is just 4. Okay, so if we're decaying, we're going to subtract the value from 1. So our A value is going to be 1 minus our decay rate, 0.13. So that gives us 0.87 for the first one. Second one, we have growth. It's going to be 1 plus 0.0345, which gives us our answer right here. So third one, very similar. It's decay, so you're going to subtract 0.03, or 0.003, pardon me, from 1. You're going to get 0.997. And here, growth by 400%, you're going to be 1 plus that growth rate, so 1 plus 4 to give you 5. Okay, that's how you're going to get the base of all of your powers. Now, going backwards, we're told if we're given the decimal, so 0.72 is going to be our A value. It is less than 1, so it's going to be a decay. So 1 minus our decay rate is going to be 0.72, and you would need to solve for R. Okay, so the algebra is not too bad here. Subtract 0.72 from each side, add R to move R over to the right side, so you get 1 minus 0.72 equals R, so R is 0.28. Okay, so that gives you our decay rate as a decimal. You have to multiply it by 100 to get it into a percentage. So multiply it by 100%, and that's what gives us our decay by 28% here. Okay, and that's going to be our general sort of steps that we're going to follow here. So here we're given, again, our base. It's greater than 1. So 1 plus our growth rate is going to be equal to our base, 1.615. Okay, so again, we solve for R. Subtract 1 from both sides of the equation, so we get R equals 0.615. Multiply that by 100% to get it into a percentage, and we get growth by 61.5%. Okay, so just follow the same idea for the next one. So 1 minus R equals 0.817. Okay, solve for R, turn it into a decimal. So here 6.25 is growth, so 1 plus R is 6.25. Solve for R, turn it into a percentage, and you've got your answer. Okay. So now let's look at some more word problems here. So we're told here in 1950 population was about 2.5 billion. It was double that in 1987. Assuming that growth is going to be exponential, so it's growing by a common ratio every single year. What is the annual growth rate? So again, same idea as when we did day 1 of this lesson. Y equals C times A to the X is going to be our starting point. We got to figure out what goes where inside the equation. So at the start, in our first year here in 1950, the population is about 2.5 billion. So our starting population is 2.5 billion. That's going to be our C. Okay, I'm not going to use billions here, so we'll just use 2.5. Now, it was double that in 1987. So we're comparing 1950 to 1987. So how many years is that? Subtract 1987 from 1950. That's 37 years. So that's going to be our X value. And if we start at 2.5 billion and it wound up doubling in 1987, so in 1987 we'd have double our starting population, so we have 5. Okay, and we're looking for the annual growth rate, and the annual growth rate would be part of our base of our power, so we're actually looking for A. Okay, and if you want to, you can immediately start by putting 1 plus R in the equation for A, or we can solve for A first. I'll probably find easier to solve for A first, and then we'll try to find our growth rates from there. Let's put everything we know into the equation first. So Y is 5, C is 2.5, and we have some A value that we don't know, the exponent of 37. Okay, so I'm going to do first here, I'm going to get the A to 37 by itself. I'm going to divide both sides of the equation by 2.5. So 5 divided by 2.5 is 2. So we have something to the exponent 37 equals 2. So how do we get rid of that exponent? Well, we're going to take that root of the equation. So to get rid of that 37th exponent 37 will be the 37th root of that side of the equation. So we're going to do the 37th root on this side as well. Okay, so if we're just looking for what A is, it's going to be whatever the 37th root of 2 is. And you can do that in your calculator, or you can rewrite this as 2 to the exponent of 1 over 37, whatever you find easier. So you run that through your calculator and you should get, I'm going to keep it a lot of decimal places here just so I can keep this going here. So I have 1.01891. Okay, so that's going to be my A value. So if we want the actual growth rate, it's not A we want, it's R. So since this is growth, A is going to be equal to 1 plus my growth rate. So I need to go through that extra step to solve for r. So just subtract 1 from both sides of the equation. So I get r equals 0.01891. So that's my growth rate. It is as a decimal. I want to turn to a percentage, so I'm going to multiply that by 100%, which should give me a final growth rate of approximately 1.9% per year. Okay, so one thing to remember, whenever you're solving for growth rate, solve for the base of that power first, and then once you have that, you can look for either the growth rate or the decay rate. If it's decay rate, we would use 1 minus r instead of 1 plus r. But again, once you have that base, you could then solve for r using whatever the appropriate method is. Okay, so let's take a look at something a little bit different. So again, these problems are getting a little bit more complicated here. So we have a population that triples every 3 years. How large will a population of 1024 be after 26 years? Okay, so this one's a little bit different. Now we're starting. We're going to start with y equals c times a to the x. So that is not changing. Okay, so we have population tripling every 3 years. So if it's tripling, we're going to use for our base, the base of our power, 3, which seems to make sense. Okay, we start with a population of 1024, so that's going to be my c. Okay, and we're looking for the final population. Okay, after 26 years, so final population we're looking for, that's y, that's our unknown. Now, where this can be a little bit tricky, it says we want to find out how large the population will be after 26 years. Well, it's going to be very, very tempting to put 26 in for x. Okay, but let's just think about what would happen if I did that. So if I have y equals some initial value, 1024. Let's try that again. 1024. Okay, base of 3 and exponent of 26. Now, if I have 3 to the exponent of 26, I am saying that in 26 years, in my 26-year time period, the population is tripling 26 times, right? Because it's 3 to the exponent of 26. However, it's not tripling 26 times in 26 years because it only triples every 3 years. So we have to take that into consideration here. It's not tripling every year, only every 3 years. So it's not tripling 26 times, it's actually tripling every 3 years, so it'll be 26 over 3 times that it triples. The number of times it triples will be 26 years divided by 3 because it triples every 3 years. So our x value is going to be 26 over 3. Okay, so be very, very careful when it says it triples not every year, every 3 years. Our time period needs to be divided by 3 because it's only tripling every 3 years over that time period. Okay, so once we have this, it's nice. Y is already isolated, so we can run this through our calculator, and we should get, once we have this, a y value of, or population, a final population of 13,974,968. Okay, so again, a little bit different here, same idea, except we just have to be very, very careful with our exponent. Okay, so with that in mind, I'd like you to try this one right here. Same idea, we have something tripling every 3 years. Try and set up yourself using y equals c times a to the x, and we'll run through it together when you're ready. Alright, so take a look at your answer. You should have wound up with an initial population of 5. So just to recap here, again, we're tripling, so our base of our power is going to be 3. Our final population is going to be this 2,657,205. We're looking for the current populations, that's our initial value, that's c. Now, we have 36 years, but we can't put 36 as the exponent because it doesn't triple every year, it triples every 3 years. So we divide our exponent, or our number of years, 36, by 3, because it's only going to triple 12 times in 36 years. So 36 divided by 3 gives me 12. That's my new exponent here on 3. And I isolate for c by dividing both sides of the equation by 3 to the exponent 12. When I run that through my calculator, I get 5. Okay. So a couple more examples left, but we're going to have to finish this up in part 3, so we'll see you over there. Okay, now in the meantime, though, you could actually try 7c. It's another population problem, and again, we'll take it up when we see you there in part 3.